Tonight, we're going to explore one of the most seductive escape plans in the history of human civilization. Mars has become something more than a destination. It is often imagined as humanity's second chance, a place waiting beyond Earth where civilization could begin again if our own world ever became too damaged, too unstable, or too difficult to save. And at first glance, the idea is surprisingly persuasive. Mars has familiar-length days, enormous stretches of open land, buried water ice, sunlight, seasons, and an atmosphere containing materials future settlers could potentially use. We have already landed machines there, driven across its surface, drilled into its rocks, and mapped much of the planet from orbit. From a distance, it can look less like an impossible world and more like an engineering project waiting to begin. But sending humans to Mars is one problem. Moving humanity to Mars is something else entirely. At that scale, the dream begins to unravel. Human beings have never had more than 20 people in space at the same time, roughly the size of a crowded family gathering. Moving 8 billion people would mean multiplying that record about 400 million times. And unlike Earth, Mars would provide almost nothing for free. Breathable air, drinkable water, food, shelter, heat, electricity, sanitation, medicine, radiation protection, and even the pressure around the human body would all depend on systems that could never be allowed to stop working. What sounds like an escape from a damaged planet begins to look like an attempt to rebuild an entire planetary civilization inside machines. And that is why moving humanity to Mars would not simply be difficult. It could become a disaster on a scale unlike anything our species has ever attempted. By the end of tonight, you're going to understand why the simultaneous spaceflight record hides a planetary evacuation gap, how Martian ice and air become fragile utilities, and why repairing Earth's living systems remains more achievable than rebuilding them from nothing. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The first thing this plan offers is a world that seems close enough to reach. When Earth feels fragile, Mars becomes more than a red point in the sky. Environmental destruction, warming, and extinction can make our own planet feel like a ship taking on water. Spaceship Earth has carried us through every human story, but a ship can feel less secure when its crew has damaged the systems that keep it alive. Among the worlds near us, Mars offers the most convincing alternative. It is visible. We have sent machines there. Its day is familiar. Its seasons have a rhythm we recognize. Compared with the Moon, Mercury, or Venus, it looks almost welcoming. That first impression matters. Mars is not an absurd destination. It is the least impossible neighbor. The Moon may become a stepping stone, but it has no air. Mercury is closer to the Sun and far too hostile for a home. Venus waits beneath sulfuric acid clouds at about 464 degrees Celsius, hot enough to turn an oven into a cold room by comparison. Its pressure is about 93 times Earth's, like carrying the weight of a deep ocean above you. Beside those worlds, Mars can look gentle. Then comes the most persuasive number. Mars is roughly half the diameter of Earth, yet it has nearly as much total surface area as all the dry land on Earth. The reason is simple. About 71% of Earth is covered by ocean, nearly 3/4 of the surface. Set that beside 8 billion people, the whole human family, and the picture seems to form by itself. An empty world. A continental answer. Room to begin again. But here is where it gets strange. Area is not capacity. A map is not a home. Geography is not habitability. A place for a durable settlement needs many conditions at once. The ground must be safe enough to land on and build upon. The elevation must work for entry and landing. Ice must be close enough to reach. Sunlight must be useful. Temperatures and dust must be manageable. Construction must be practical. No one has established what fraction of Mars meets that whole list. The empty area on the map is real. The usable settlement area remains unknown. Water carries the same promise. Mars has polar ice and ice within rock and soil. The source claim says that all of it could equal enough water to cover Mars to a depth of 1 to 2 kilometers, a layer as deep as a mountain valley. But that is a qualified claim, not a proven municipal reservoir. It does not identify one accessible supply, its purity, or the machines that could deliver it. Some mapped candidates may sit only 2.5 centimeters below the surface, about the thickness of a coin. In parts of Arcadia Planitia, ice may lie within about 30 centimeters, the length of a school ruler. Those are encouraging places to investigate. Other deposits are something very different. In Utopia Planitia, one deposit may be 80 to 170 meters thick, as tall as a tall building or more. It may be 50 to 85% water ice, but it lies beneath 1 to 10 meters of soil. That is not a tap. It is a mine. A stock compared with Lake Superior can sound almost limitless. Yet, a Lake Superior-sized inventory, buried in dirty material, still needs prospecting, excavation, heating, cleaning, storage, pipes, power, and repairs before it becomes a glass of water. And then, there is the air. Mars has weather. It has clouds, winds, and an atmosphere made mostly of about 95.3% carbon dioxide, with 2.7% nitrogen and 1.6% argon. But its pressure is less than 1/100th of the average pressure on Earth. The molecules are useful feedstock, raw material for machines. They are not breathable public air, not an open sky, a chemical inventory. The cold sharpens that difference. The average temperature is around minus 53 degrees Celsius, colder than a household freezer by a vast margin. Cited extremes range from minus 128 to 27 degrees Celsius. Mars can offer a mild afternoon in one place and a deep polar cold in another. Neither changes the central fact. Outside, the planet does not keep a human body alive. Its rhythm is still familiar. A Martian day lasts about 24.6 hours, close to the 23.9-hour comparison for an Earth day. Its axial tilt, the angle that gives a planet seasons, is about 25 degrees near Earth's 23.4 degrees. A Martian year lasts 669.6 sols, or 687 Earth days, nearly 2 Earth years. These are real comforts for clocks and routines. They are not life support. Mars is also about 1.5 times farther from the Sun than Earth. It receives about 43% of Earth's sunlight, less than half the light available to a solar panel or greenhouse on our world. Then dust settles, seasons change the angle, panels foul, electricity must be stored, crops need controlled warmth and sometimes artificial light. Sunlight exists. Dependable grid power is another problem. Rovers add a final layer of confidence. They have crossed this landscape, tested rocks, and sent back images that make Mars feel increasingly familiar. SpaceX has made Mars a stated ambition. The source places a claimed 2026 valuation near $1.7 trillion, compared with an inflation-adjusted Apollo figure near $300 billion. More than 5 times Apollo sounds like momentum, powerful enough to change history. Wait, financial momentum is not an evacuation system. Apollo estimates vary by scope and year. A historical figure was $25.4 billion in 1973 testimony. Later reconstructions produce very different totals. As of August 2026, a June 2026 securities filing used $135 per share for a fee calculation and listed an $85.25 billion maximum aggregate offering figure. That figure was not a stated company valuation. It was not a Mars budget. It covered several businesses, not a funded plan to move humanity. So the package is real. Space, ice, air, light, seasons, machines, money. Each is a beginning. None is a replacement Earth. And the largest part of the dream has not yet been touched, moving 8 billion people. But moving people is a different problem. Before asking what waits on Mars, it helps to ask how many people our space age has ever carried. The answer depends on where we draw the edge of space. Some organizations use 100 kilometers above Earth. Others use 80.5 kilometers, also called 50 statute miles. Other databases use another threshold above 80 kilometers. That difference is about the distance between neighbouring towns. It changes who enters the count. There is another complication. Some totals count every ride. Others count each person only once. A person who crosses the boundary twice can become 2 entries in one ledger and 1 person in another. So there is no single boundary neutral census of human space travelers. We do not know the perfect total because the question itself has more than one definition. The source uses one careful baseline. It says 781 people had left Earth and touched space. That is fewer people than a modest theatre audience. SpaceX had carried 78 of them through Dragon over 6 years and 20 missions. Those figures matter. They show real progress. But they are source-defined figures, not a final answer to every counting question. The more relevant number is smaller still. Only 24 people have travelled beyond low Earth orbit. Low Earth orbit means the region close enough to Earth for stations to circle the planet. 24 people is one small classroom. Every one of them travelled through the Apollo lunar missions. No human has travelled to Mars. That is the historical flaw beneath the dream. We have sent people above Earth. We have sent a few people beyond its immediate neighbourhood. We have never carried a human population between planets. Rocket launches can make that difference easy to miss. A launch schedule looks busy. SpaceX completed 96 launches in 2023. It completed 134 in 2024. The source states 165 launches in 2025. That is nearly 1 launch every 2 days. It can feel like a bridge is already being built. But most of those rockets did not carry people. They carried satellites. They carried cargo. They carried tankers. They carried test payloads. A launch is not automatically a passenger departure. A rocket rising from a pad is not automatically a family leaving Earth. The source gives about 70 people in 1985 as a historical human spaceflight scale marker. That is another small classroom. Its exact method is not supplied, so it should not be treated as an uncontested record. Still, the scale is clear. The human side of spaceflight has remained small even while the machinery around it has become more frequent. But here is where it gets stranger. The highest number of humans in space at one time is 20. 20 people in one room. That is the high watermark. The source describes a brief overlap in 2023, tied in 2024. 11 people were aboard the International Space Station. 3 were aboard Tiangong, China's orbiting station. 6 were aboard Virgin Galactic's VSS Unity during part of a suborbital flight. Suborbital means the vehicle reaches space, then comes back down without circling Earth. As of August 2026, the updated records remain 20 humans in space, simultaneously, and 19 in orbit. The second number excludes the people who merely crossed the boundary and returned. These records are volatile. Another mission can change them. But the present picture is still remarkably small. 20 people. 8 billion people. A room facing a target 400 million times larger. Not a crowded flight. A planetary gulf. Not a larger waiting area. A new kind of civilization. This is why launch frequency and passenger capacity must stay separate in our minds. We can launch machines often. We can keep crews continuously in orbit. We can return capsules safely. None of that establishes a system for moving whole communities across interplanetary space. Starship is often offered as the bridge across that gulf. The source gives a favourable range of 100 to 200 passengers. Current published design language describes up to 100 people on long-duration interplanetary flights. It also describes more than 100 metric tons to orbit. A metric ton is 1,000 kilograms, about the mass of a large car. These are design statements. They are not demonstrated human transport. And a Mars passenger is not an airline seat. A historical cabin concept imagined 40 cabins, mostly holding 2 to 3 people. It also needed a central storage volume, a galley for preparing food, a common area, and a solar storm shelter. A solar storm shelter is a protected space for bursts of radiation from the sun. Even a ship for about 100 travelers already begins to look like a closed settlement utility. It needs to make air, manage water, store food, handle waste, create privacy, provide exercise space, and protect its people. The seat is the smallest part. So let us give the idea every advantage. Start with the source's high end of 200 passengers, then multiply it by 10. Grant a Mars departure 2,000 passengers. That is 20 times the current up to 100-person design language. It is not a real proposal. It is a deliberately generous assumption. The arithmetic is simple. 8 billion people divided by 2,000 passengers per departure gives 4 million passenger departures. 4 million. Even after the tenfold gift. Spread those departures across 100 years. That becomes 40,000 passenger departures every year. Divide again. It becomes roughly 110 passenger departures every day for a century. And this is the favorable version. It counts no tanker flights, it counts no cargo vehicles, it counts no failed launches, it counts no maintenance flights, it counts no surface delivery missions. It treats every departure as full, successful, and ready for Mars. Compare 40,000 annual passenger departures with the source stated 165 launch year. The generous model needs roughly 240 times that benchmark every year, for 100 years. And it needs all of those launches to be vastly more demanding than the launch record they are being compared with. This is not an undersized lifeboat waiting for more passengers. It is a lifeboat system that would need to become a permanent planetary transport industry. Pads, factories, crews, fuel, ships, hospitals, training, repairs, landing systems, a chain that must keep working for generations. The more conservative version is harder still. Give each departure 200 seats. That already doubles the currently stated 100-person interplanetary capacity. Now the target needs 40 million departures. Over 100 years, that is 400,000 per year. The numbers do not become gentler when the seats become more realistic. They become harsher. There is real ambition in the movement from 20 people simultaneously in space to a conceptual ship for 100. We should not dismiss that ambition. It may lead to important voyages, outposts, and discoveries, but conceptual capacity is not demonstrated throughput. Throughput means how many people a system can move safely, again and again, year after year. We do not know whether a 2,000-person interplanetary life support system can work. We do not know its loss rate. We do not know the capacity of launch ranges, the places rockets leave from. We do not know what passenger flow could be sustained for centuries. We do not know what kind of reliability that system would require. The scale gap is not a matter of adding more rockets. It is not even a matter of building one larger rocket. It is the distance between rare, carefully selected crews and the migration infrastructure of an entire species. And even this is only the seat count. The next constraint is the slow clock between worlds. The clock does not run one day at a time. That daily average assumes the planets cooperate every day. They do not. Earth and Mars move on different paths around the Sun. The most efficient chances to leave Earth for Mars return about every 26 months. That is more like a train arriving once every 2 years than an airline schedule with a morning departure. A century sounds long. It is long in a human life. But in this particular schedule, it contains only about 46.15 useful cycles. Fewer than 50 waves. That is the second denominator hidden inside the first. We already gave each departure 2,000 passengers. We already found that 4 million departures were needed. Now divide those departures amongst about 46 opportunities. The result is about 86,667 passenger ships in every opportunity. The source rounds the same picture to roughly 87,777 launches across 46 windows. This is not a steady flow. It is a surge. It is a surge repeated 46 times. At 200 seats per departure, the burden rises to about 866,667 departures in each opportunity. So let us make another extravagant gift. Imagine a ship carrying 20,000 people. No verified design exists for such a ship. Still, even this imagined vessel needs about 8,667 departures during every Mars opportunity. And that count assumes every day in the opportunity can support the chosen route. We do not know that it can. But here is where it gets strange. The calendar is only part of it. A ship cannot simply return from Mars, refuel, and leave again next week. Efficient one-way journeys commonly take 6 to 9 months. That is most of a year inside one vessel. Conjunction studies of the orbital timing between the planets, use outward journeys around 180 to 260 days. Some take as long as 300 days. Then the ship may remain near Mars for 300 to 500 more days, while the geometry becomes favorable for a low-energy trip home. The vehicle is reusable. The route is not. It waits. It drifts. It misses the next train. Owning a reusable train does not help much when the track aligns only once every 2 years. Reuse can reduce the number of holes we build. It cannot make Earth and Mars line up more often. The planet positions set the rhythm. The fleet must live with it. The source tests this with another favorable image. It uses a suggested fleet of 1,000 ships, each carrying 100 passengers. Under the dispatch assumptions in that model, moving humanity would take 300 years. That is not a normal planning horizon. It is longer than recorded civilization by many times. The exact total belongs to the source model. The structural point is firmer. Seats, fleet size, and the rare launch opportunities govern the calendar together. So the next gift becomes even larger. Give the plan a 20,000 person spacecraft. Think about Icon of the Seas. It is about 365 meters, or 1,200 feet, long. That is longer than 3 football fields laid end to end. It weighs around 250,000 gross tons and carries about 10,000 crew and passengers. A Mars ship in this thought experiment carries twice that population. Then, we stand the comparison on end and launch it into deep space. That is the scale of the imagined vehicle, not a larger airliner. A moving district. Even then, 8 billion people require 400,000 departures. Spread across 100 calendar years, that is about 11 giant ships each day. And the calendar is still misleading us. The source uses a 200-day journey out and a 400-day round trip. With the long wait that can miss the next 26-month opportunity, it estimates a fleet of 17,390 such ships. This is source-modeled arithmetic, not a verified operations plan. No human-rated design exists for one ship of this kind, much less a fleet of thousands. Viewed by the actual opportunities, the burden does not arrive as 11 orderly daily launches. It gathers into about 8,167 departures when the route opens. That is a moving city of ships trying to leave within a limited season. The familiar daily average has hidden the traffic jam in the sky, and the ship arrives somewhere. That part has not been solved either. Each arrival brings 20,000 people who need pressure holes, radiation shelters, landing systems, hospitals, kitchens, sanitation, exercise areas, spare parts, crew quarters, places to handle death, and infrastructure waiting on Mars before the passengers step outside. The giant ship reduces a number. It does not remove the civilization that must receive it. The passenger number also conceals the launches behind the launch. Mars-bound Starship concepts use orbital refilling, moving propellant from tanker vehicles into the departing ship while both are in low Earth orbit. A historical architecture from 2016 suggested 3 to 5 tanker flights for every Mars ship. That is not a current requirement. It is an illustration. But it turns one passenger departure into 4 to 6 launches from Earth before cargo-only flights are counted. Apply that old illustration to the 200-seat case. The total becomes roughly 160 million to 240 million Earth launches. Not a forecast. A warning about what a seat count leaves out. The same missing mass appears inside the ship. A reference daily ration gives each person 1.83 kilograms of packaged food, roughly the weight of 2 full bottles of water. It gives 4.17 kilograms of water consumption, a little more than 4 1-litre bottles, and it gives 0.84 kilograms of oxygen, close to the mass of a large book. These are daily inputs, not luxuries. For 200 people over 180 days, the manifest holds 65.88 metric tons of food, 150.12 tons of water, and 30.24 tons of oxygen. More than 246 tons in all. That is the mass of nearly 250 large cars before recycling machinery, tanks, shielding, cabins, medicine, clothing, spare parts, or settlement cargo. A passenger list is only the label on a cargo manifest. But the biggest pressure comes from Earth itself. The population does not pause while the ships depart. The seed uses present figures of 360,000 births and 160,000 deaths each day. That adds about 200,000 people daily. These are not a prediction for a whole century. They are a stress test using a fixed present rate. Now return to the 20,000 person ship. 11 such departures remove 220,000 people. 11 ships. Every day. Before the original target even begins to shrink. Not an evacuation. A treadmill. 10 giant ships would nearly cancel the daily growth. The 11th would barely begin the task we started with. And every one of those ships still needs its window. Its tanker flights, its crew, its cargo, and a sealed city waiting at the other end. Cost adds one final generous assumption. In 2016, an aspiration suggested eventual fares below $200,000, perhaps near $100,000. Multiply the higher fare by 8 billion people, and the ticket total reaches $1.6 quadrillion. Use the lower fare, and it is $800 trillion. Those are not program estimates. They are the arithmetic consequence of an aspiration, before cargo, settlement building, public subsidy, failures, or losses. The aspiration is often smaller and more concrete. A city of 1 million people in 20 to 30 years. Even a reduced thought experiment of 8 million people, 1,000th of the full target, needs 40,000 departures at 200 seats. At 100 seats, it needs 80,000. The smaller target is already a planetary transport project. And that is only the transport ledger. Thousands of giant vessels, factories, launch sites, propellant plants, orbital traffic control, crews, tankers, cargo. A century of global attention held without interruption. None of it has yet answered the quieter question, waiting inside every successful departure. How do the passengers stay alive once Earth has fallen away? Suppose, generously, that one of those ships has launched on time. The launch pad falls away. The fleet figures disappear, and the vehicle becomes the only place its passengers can live. For the next 6 to 9 months, it is not transportation in the ordinary sense. It is the atmosphere, the waterworks, the power station, the kitchen, gym, clinic, sewage plant, storm shelter, and home. A flight has become a closed world. The efficient journey is only one part of a longer dependence. One reference expedition uses 180 days traveling out, 500 days on Mars, and 180 days traveling back. The outward leg alone lasts about half a year, from one season into the next. The stay on Mars lasts well beyond a year. The return adds another half year. Launch is not the end of the problem. It is the beginning of an expedition that can hold people away from Earth for years. And then the shielding matters. Earth has a magnetic field and a thick atmosphere. Together, they soften part of the radiation that moves through space. Beyond that protection, the ship must provide what the planet once supplied. The Curiosity Radiation Assessment Detector, an instrument that measures radiation during travel, recorded a cruise rate of about 1.84 millisieverts per day inside spacecraft shielding. A millisievert is a measure of radiation dose absorbed by the body. Over 180 days, that rate adds to about 331 millisieverts. That is the outward crossing alone. 2 such crossings reach about 662 millisieverts before surface living is included. The source uses a reference expedition approaching 1 sievert. A sievert is 1,000 millisieverts, a larger unit for the total biological burden. The reading came back reversed. The surface is often treated as the radiation problem. The voyage is already carrying a large share of it. Not after landing. Before landing. Not after settlement. During the crossing. The exact dose is not fixed. It changes with the route, the thickness and placement of shielding, the activity of the sun, and the direction the vehicle faces. We do not know the civilian risk for every age and health condition. But radiation is not only a later cancer statistic. It may affect the central nervous system. the brain and nerves that guide thought and movement. It may affect cognition, motor control, cardiovascular tissue, and the eyes. Astronaut crews are selected for unusual health and trained for unusual conditions. A migration ship would not contain only that narrow group. It would contain children, older people, pregnant people, people with chronic illness, people with different responses to the same exposure. The ship cannot choose which bodies need care once it has left. Space inside the hull makes the same point in another way. A transit habitat concept for 4 people assigns 84.81 cubic meters for living space, 99.13 cubic meters for stowage, and 132.90 cubic meters for systems. Stowage means stored supplies. Systems means the machinery that keeps the supplies useful. Together, the concept reaches 316.85 cubic meters of pressurized volume for a mission lasting up to 200 days, more than 3 years, and 3 birthdays. That total volume is roughly the enclosed space of a small house. 4 people occupy it, yet less than a third is described as habitable. The rest is food, storage, tanks, filters, wiring, pumps, equipment, and the empty clearance needed to service them. Seats are the smallest part of the calculation. Food is not just a menu, it is a daily operation system. A planning value near 3,035 kilocalories per person each day is roughly 3 ordinary 1,000 calorie meals. Each passenger also needs more than a kilogram of packaged food and waste packaging each day, about the mass of a full 1-liter bottle of water. Multiply that by people and months, and the kitchen becomes another cargo bay. Then there is menu fatigue. The slow weariness of eating the same limited choices can lead people to eat too little. Taste becomes a health variable, not a luxury, an operations requirement. The body is another system that has to be maintained. In microgravity, the near weightless condition of orbital flight, bone can lose 1 to 2% of its density each month without effective protection. Fluids also shift upward from the legs and abdomen toward the head. That change can affect the heart and blood vessels, the eyes, and the brain. The answer sounds manageable at first. Exercise. International Space Station astronauts, people already screened and trained for this environment, exercise about 1.5 hours each day, 6 to 7 days every week. That is about the length of a feature film, nearly every day. Even then, average strength and aerobic fitness losses remain around 10 to 12%, about a tenth. Some measures show losses above 20%, more than 1/5, in 12 to 38% of crew. The gym is not an amenity. It is life support. It takes space. It takes power. It takes maintenance. And it still does not guarantee that every passenger arrives fit enough to stand and work. Mars offers 0.38 g, a little more than 1/3 of Earth gravity. We do not know whether that is enough to restore a weakened body or prevent further decline. A centrifuge, a rotating device that creates an outward push like gravity, might help. But no human-rated centrifuge has established the needed gravity level, rotation rate, duration, or frequency. It is not a solved system. It is not proven useless either. The ship also cannot rely on Earth as an emergency room. One-way communication delays range around 3 to 22 minutes, or in another published range, 4 to 20 minutes. A ground team can advise. It cannot reach a bedside during a fast crisis. It cannot seize manual control in time. Some trajectories may also have blackouts lasting several days. And then, the meaning of abort changes. An 850-day trajectory analysis, a study of one full expedition path, found that after roughly 30 days from Earth, about 1 month, every propulsion case studied needed a year or more to return. Some refueling designs may not allow an outward abort at all. The route does not bend back like a road trip. It carries the ship onward. A safe haven can keep people alive for a few days while they handle fire or depressurization. That can matter enormously. But it is a storm cellar inside the damaged house, not a lifeboat home. Exterior repair through an airlock may be the only answer, with no harbour and no nearby rescue ship. Selected crews already treat behavioral health and teamwork as formal risks while living in spaces comparable to a studio apartment. Add thousands of civilians, and the unanswered work expands. Infection, disability, conflict, pregnancy, death, sanitation, unequal privacy, policing. No verified architecture has shown how all of that works inside a ship moving through deep space. The mass evacuation premise fails twice before anyone reaches Mars. First, it cannot launch enough people. Second, it cannot yet turn each launch into a self-repairing city with shielding, medicine, exercise, sanitation, repair, and dependable rescue. And the pressure vessel waiting at the destination will not make that condition disappear. Landing changes the view. It does not change the basic condition. Suppose the ship survives the crossing. Suppose it lands safely. The passengers have reached Mars, but they have not reached ordinary ground. The surface supplies no breathable pressure, no liquid public water, no food, no clean outdoor air, no steady warmth, no dependable radiation shelter. It supplies a place to build those things. That difference matters. A Mars settlement would still be a pressure vessel. It would simply be a pressure vessel resting on red soil. The air makes this clear. Average Martian surface pressure is about 5.6 to 6 millibars. Earth averages 1,013 millibars. That is like taking almost all the air from a room and expecting the room to remain a public space. In deep basins, the pressure can approach 9 millibars. At the summit of Olympus Mons, it falls to about 1 millibar. Location changes the number. It does not change the condition. This is not high mountain air. It is near vacuum. One technical reference gives atmospheric oxygen at about 0.13%. The rest is mostly carbon dioxide, a gas machines can process but lungs cannot use. Outside, a person needs pressure, oxygen, cooling, water, monitoring, controls, and communication. A spacesuit is not clothing. It is a personal spacecraft, and the margin is short. A documented chamber accident left a person conscious for about 14 seconds. Less time than it takes to cross a small room. The body does not burst apart as films sometimes suggest, but useful action disappears quickly. A damaged seal is not a dramatic inconvenience. It is an immediate systems failure. Cold adds another permanent job. Mars averages about minus 53 degrees Celsius. Conditions can fall near minus 128 degrees Celsius, then rise toward 27 degrees Celsius in favorable equatorial midday conditions. Every pipe needs thermal control. Every battery does. Every seal, vehicle, greenhouse, hospital, and water line does. The outdoor world is not a background. It is a continuous load on every machine. Water follows the same pattern. Some ice may lie shallow beneath the surface. Other deposits sit below meters of overburden, the soil and rock resting above them. The old picture of drilling 10 kilometers everywhere is too simple, but the correction does not make a water utility appear. No deposit arrives at a tap. It must be excavated, heated, captured, purified, stored, pumped, protected from freezing. Surface pressure is too low for stable liquid water, so each liter has to remain inside a managed system from the mine to the cup. Ice is an asset. It is not a city waterworks. Then comes the dust. It is easy to picture Martian dust as ordinary dirt, a nuisance on boots and solar panels. The material may be much harder to live with. Candidate hazards include perchlorates and chlorates, reactive salts that can damage health and equipment. They include silica, a mineral dust that can irritate lungs. They include nanophase iron oxides, extremely small iron-rich grains, gypsum, and debated traces of other metals. Fine particles can enter the lungs. Some may enter the bloodstream. Oxidizers can corrode machinery. They can contaminate water and crops. And authentic airborne Martian dust has never been returned to Earth for full laboratory testing. That last fact should make the language calmer, not easier. As of July 2026, a proposed crew exposure limit remained preliminary. It draws on dust simulants, rover and lander measurements, and lunar toxicology. the study of how lunar material affects living tissue. We do not know the final risk for a population living there for decades. Uncertainty is not permission to relax. It is a reason to contain. Airlocks help. Suit ports help. Neither makes dust vanish. A suit port is a connection that lets a suit remain outside the habitat wall while its wearer climbs in. But machinery and supplies still have to cross the boundary. Dust-laden carbon dioxide may need to be pumped away before repressurization. The return of breathable pressure. Pre-filters protect pumps and cabin filters. Sealed bearings, the smooth-moving rings inside joints, must protect wrists, shoulders, hips, thighs, and ankles in suits pressurized above 4 psi. Dust reaches everything: lungs, seals, bearings, filters, crops, radiators, solar panels. The same settlement must also replace another service Earth supplies without asking: radiation protection. Mars has no global magnetic field, the planetary shield that turns away many charged particles from the sun and deep space. Its thin atmosphere adds little shielding. At Gale Crater, Curiosity measured surface radiation around 0.6 to 0.67 millisievert each day. A millisievert is a measure of radiation dose, weighted for its likely effect on the body. Earth's global natural background is about 2.4 millisieverts in an entire year. Mars can deliver that yearly Earth background in about 4 days. A common occupational benchmark is 20 millisieverts per year, averaged over 5 years. At the Gale Crater rate, that amount arrives in little more than a month. The often repeated claim that Mars radiation is 100 times Earth's natural background is only broad framing. The ratio depends on place, shielding, solar activity, duration, and which units are compared. The precise ratio moves. The practical problem does not. Ordinary residence becomes continuous occupational exposure. On May 20th, 2024, that background condition changed sharply. Curiosity recorded 8,100 micrograys at the surface during a solar event. A microgray measures absorbed radiation energy. The contemporary comparison was about 30 chest X-rays. In orbit, the same storm was described as an exposure equal to 200 normal days in 64 hours. That orbital number is not the surface measurement. The distinction matters. Both numbers point to the same requirement. People need somewhere deeper to go. The simple answer seems to be dirt. Cover a habitat with regolith, the loose, broken material that blankets the Martian surface. It does help. The first 15 to 20 centimeters produce a strong early reduction in dose. After about 20 grams per square centimeter, the benefit against galactic cosmic rays, high-energy particles arriving from beyond the solar system, begins to diminish unless much more mass is added. Not a thin cover, a permanent structure. Habitat studies consider layers 50, 75, and 100 centimeters deep. That is a half meter, 3/4 of a meter, and a full meter of material that must be excavated, hauled, placed, retained, inspected, and repaired. Even then, designs retain dedicated storm shelters. The shielding has to work around airlocks, radiators, cables, exits, and buried pressure walls. It becomes civil engineering that never ends. And then the sky itself can remove the power margin. Thin Martian air limits the force of wind. A storm is unlikely to blow a habitat apart. That sounds reassuring. It is not the important part. In 2018, optical depth rose to 4.9 in 3 sols. Optical depth is a measure of how much dust blocks light passing through the sky. 4 sols later, a virtual blackout followed. Opportunity could no longer recharge. Insight also entered safe mode after dust fouled its panels. Not blown down, powered down. Not a hurricane emergency. A power emergency inside a sealed world. The dust can dim solar arrays. It can foul exposed mechanisms. It can obscure navigation and complicate heat rejection, the process of shedding unwanted heat. Surface work can stop just when repairs are most needed. And every enclosed room depends on power for air, water, warmth, food, communication, and light. This is what the Mars image leaves out. Billions of people would not spread across an open second planet. They would occupy connected pressure compartments, suits, tunnels, and shielded rooms. A submarine population, one that never surfaces. Outside is vacuum. Outside is cold. Outside is radiation. Outside is toxic dust. And once those compartments are sealed, the next question is whether their air, water, and waste loops can keep working. The walls only hold a space. Something still has to keep that space alive. Inside a Mars habitat, air and water would have to keep moving, hour after hour, through pipes, tanks, filters, valves, and machines. The shell separates people from the surface. The loops separate them from slow failure. Earth performs much of this work without being noticed. The atmosphere dilutes the products of breathing. A watershed carries water onward. Soil and living systems absorb waste. Factories replace worn parts. The wider world takes heat, humidity, leakage, contamination, and equipment wear, then spreads the burden across an entire planet. Mars offers none of those buffers. Every breath remains part of an inventory. Every lost liter leaves an inventory. Every worn seal becomes a task for someone inside the walls. Water is the clearest example. A habitat would collect urine. It would collect humidity from breath and sweat. It would collect water from suit systems. Then it would send that mixed stream through distillation or brine processing, separating water from dissolved material. Through multi-filtration beds, layers that trap unwanted chemicals. Through catalytic oxidation, a reaction that breaks down contaminants. Through conductivity checks, tests of how readily the water carries electricity. Then through reprocessing and storage. It is a municipal treatment plant inside a pressure vessel. The achievement is real. In 2023, a station demonstration raised total water recovery from 93 or 94% to 98%. That is remarkably close to a circle, but it is not a circle. From every 100 pounds collected, 2 pounds remain lost. 2 1-pound cans, gone from the loop. At small scale, that loss can sound manageable. At city scale, it becomes a steady requirement. More ice must be mined. More water must be imported. More reserve must be held back for the day another machine stops. And the accounting is not even settled into one clean figure. Public descriptions in April 2025 also described current recovery as around 90%. About 9 parts returned from every 10 collected. The two figures may describe different hardware or different system boundaries. A demonstration is not necessarily the same thing as everyday operation. We do not know yet which boundary a Mars city could reliably sustain. The important phrase is almost closed. Oxygen follows the same path. An oxygen generation assembly uses electrolysis, splitting recovered water with electricity into oxygen and hydrogen. The oxygen returns to the cabin. The hydrogen can be sent into the Sabatier process, a chemical loop that combines it with the carbon dioxide people exhale. The result is water and methane. The water can return. The methane does not. Current station systems vent it. And state-of-the-art descriptions recover no more than about 50% of the oxygen bound in carbon dioxide. Half the oxygen in that stream can come back. The rest still has to be supplied by water, machinery, power, and replacement parts. Not failed chemistry, almost closed chemistry. Carbon dioxide itself must be removed before it builds up in the air people breathe. That takes molecular sieves, materials with tiny pores that trap selected gases. It takes sorbent beds, replaceable materials that capture carbon dioxide. Fans move the air. Heaters regenerate the beds. Valves direct the flow. Controllers read sensors and command the equipment. Charcoal and catalytic oxidation handle other unwanted compounds. Backup equipment waits behind the first line. The future cabin target is below 3.0 millimeters of mercury. That is a pressure scale named for a liquid column only a few millimeters high, about the width of 2 stacked coins. Reaching that number is not the work of a forgotten filter. It is the work of an active machine, every day. And active machines leave records. In 2013, a stalled valve used the final spare aboard the station. In 2016, fan motor controllers, heater controllers, and an air selector valve required replacement. In 2017, zeolite, The mineral inside a gas-trapping bed broke into dust and restricted airflow. The sited adsorption beds could last more than 3 years before replacement. More than 3 years is useful. It is not permanent. Then came June 2024. A urine processing pump failed, and no replacement pump was already in orbit. Waste had to be stored abnormally until a cargo flight brought the missing part. The station endured. Earth experts could diagnose the problem. Earth had made the pump. Earth could send the pump. That is not a criticism of the station. It is the lesson of the station. A Mars settlement would have less margin. A cargo delivery may wait for the next launch opportunity. The replacement part may depend on a factory that does not exist there. And a city cannot place its entire water system into abnormal storage while it waits. The same is true for backup systems. It is tempting to say that a second unit solves the danger. A second unit helps, but it needs its own pumps, valves, beds, controllers, filters, software, power, technicians, and spares. A shared contaminant can reach both units. A shared power loss can stop both units. A bad software update can confuse both units. More people bring more hands. They also bring shared pipe grids, shared pressure zones, and larger consequences when one assumption fails. Then, the loop becomes biological. Plants can use crew carbon dioxide. They can provide oxygen and food. They can recycle water. But roots still need oxygenated water and nutrient salts. Mars regolith, the loose material covering the ground, lacks organic matter. Perchlorates, reactive salts in the soil, must be reduced or removed before that material enters a crop loop. Waste does not disappear either. It becomes a chemical and biological problem. Wastewater samples have shown 100,000 to 1 million colony-forming units per milliliter. A colony-forming unit is a living cell or small group, capable of growing into a visible colony. A milliliter is less than a teaspoon. In that small volume, the biological load can already be substantial. Potable water checks in flight may be periodic rather than continuous. A city would have to find pathogens, organisms that cause disease, biofilms, thin microbial layers on wet surfaces, corrosion, toxins, nutrient imbalance, sensor drift, all across a distribution network larger than any spacecraft. This is where scale changes the picture. A handful of specialists can watch a handful of tanks. A city needs treatment plants, quality laboratories, isolation valves, reserve gases, emergency water, spare capacity, and crews trained for every shift. Billions would require an artificial planetary metabolism, a system that circulates air, water, nutrients, waste, heat, and parts because the planet outside circulates none of them for free, and the failures can join together. A power shortage slows pumps and heaters. Lower flow weakens water treatment and carbon dioxide removal. Bad air or contaminated water increases medical demand. Illness reduces the maintenance staff. Delayed repairs consume the reserves. Rationing begins. Then a second fault arrives. That is the real danger. Not one dramatic break. A chain of ordinary burdens. On Earth, a city can draw from another watershed, grid, factory, or hospital. On Mars, replacement hardware may be months or years away. No universal reserve duration exists for a Mars city. No spare percentage has been validated. No biological system has demonstrated complete closure of food, nutrients, gases, water, and waste at settlement scale. Almost closed means survival, while storage, spares, labor, and outside support stay ahead of loss. There is one place on Earth where people already try to live that way. That place is Antarctica. It is probably the closest honest analog we have. Small crews live in intense cold. Their buildings are enclosed. Their inventories are planned far ahead. Their specialist staff cannot simply walk away when a machine fails. Access comes with the seasons. Much of what keeps the station alive has to arrive before winter closes in. And Antarctica proves something important. People can endure extraordinary isolation. They can maintain equipment. They can share a small artificial world for months. But the station has one advantage that is easy to overlook. It is still on Earth. Ships and aircraft can bring food, fuel, parts, replacement staff, and medical evacuation. The industries behind those ships breathe ordinary air. They use ordinary gravity. They draw on oceans, farms, mines, factories, hospitals, and a global economy. The outpost is remote. The planet supporting it is not. That difference begins with food. One source benchmark uses 780 kilograms of food per person each year, roughly the mass of a compact car. It should not be treated as one universal Antarctic rule, but it gives the scale of a recurring supply problem. Station chefs may plan around a single annual delivery, then keep a crew fed for as long as 18 months. A full year. Then another half year. The food has to be there before the isolation begins. McMurdo makes the larger system visible. In a summer week, it can support as many as 1,100 people, more people than a large school. In winter, that falls to 200, a small audience. Yet its annual operation has served 147,956 meals, enough for about 400 meals every day. It has used 1,418,600 gallons of fuel, enough to fill more than 2,800 standard fuel tanks. It has produced 370,000 gallons of water, about 16 Olympic swimming pools, and it has handled 4,827 pounds of waste, more than the mass of 2,000 small cars. That is not a failure of the station. It is the shape of a supplied industrial camp. Food arrives. Fuel arrives. Parts arrive. Waste is handled through a system that is ultimately connected to the rest of Earth. Other stations show the same logic at smaller scale. Concordia supports up to 16 people in 1,000 square meters, an area smaller than a third of a football field. It normally runs 2 of its 3 diesel generators, keeping 1 in reserve. It recycles washing and cooking water. It melts protected snow for drinking. Even 16 people need redundant power, stored fuel, maintained machines, and a source of water beyond their walls. The South Pole Station offers another useful caution. Source figures describe up to 150 people, a few hundred kilowatts of average power, and about 1.7 million litres of fuel each year, enough to fill roughly 700 home heating oil tanks. Wind supplies about 1/5 of the needs at 2 stations. That contribution matters, but it sits inside a larger fuel system. Renewable power reduces the delivery burden. It does not make the outpost independent. Then there is the greenhouse case. This is where the comparison becomes more hopeful. In 2018, one operator at Eden ISS grew 268 kilograms of edible fresh biomass in 286 days, nearly 10 months, from 12.5 square meters, about the floor area of a small bedroom. The system produced 26 crops, more varieties than many home gardens manage. Divided across 10 crew members, that is about 27 kilograms each. It is only about 3.4% of the 780 kilogram food benchmark. The answer was stranger than expected. The first number sounds like a farm. The crop mix tells a different story. 67 kilograms were cucumbers, 56 were lettuce, 49 were leafy greens, fresh vegetables, valuable vegetables, not a complete food system. The greenhouse did not provide all the calories, it did not provide all the protein, it did not provide all the fats, it did not replace storage, milling, cooking, packaging, or staple crops. It supplied fresh food, crew well-being, and knowledge about how crops behave in a harsh place. That is a real achievement. It is a salad garden attached to a station. It is not a town feeding itself. Its inputs show why. The cultivation hardware used about 55 kilowatt hours, roughly the yearly electricity use of 5 average homes. That was about 205 kilowatt hours for each kilogram of fresh produce, as much electricity as a 1 kilowatt heater uses in more than 8 days. Common equipment was excluded. The operator spent 858 hours working on the system, more than 5 full-time months. That works out to about 21 hours each week, more than half a typical work week, or 3.2 labor hours for every kilogram. None of this dismisses controlled agriculture. It locates what the experiment proved. A greenhouse can deliver fresh food, it can support morale, it can test crop operations, but its staple calories, power systems, replacement parts, staff, and emergency support still come from the world around it. Mars begins without that world. Its regolith is broken rock. It has no organic matter. It has no balanced ecology of nutrients and living organisms. Perchlorates are reactive salts in the ground that require treatment. Brines, very salty water, add another processing burden. Simply adding water would not turn that material into a field. Hydroponics avoids soil by growing roots in managed water. Aeroponics sprays roots with a nutrient mist. Both are useful methods. Neither removes the industrial work. They still need nutrient minerals, pumps, lights, reservoirs, sterilization, seed stock, pest control, carbon dioxide control, humidity recovery, and people who can repair each part. Now comes the scale calculation. At the source benchmark of 780 kilograms per person each year, 8 billion people would need 6.24 trillion kilograms of food. That is 6.24 billion metric tons, a stream of 1 kilogram parcels repeated more than 6 trillion times. The figure is import mass arithmetic, not a designed diet, but it shows the quantity a Mars food system would have to grow, process, store, and protect every year. Crop area makes the same point more clearly. A planning value of about 50 square meters per person, roughly a small apartment floor, becomes 400,000 square kilometers for 8 billion people. That is about 1.64 United Kingdoms of controlled growing area. A high-yield wheat case can approach 30 square meters per person, about a small studio floor. But wheat alone is not a varied diet. It is not a failure-tolerant diet either. And stacking does not make the burden disappear. Vertical farms shrink the map footprint. They do not shrink the illuminated crop area. Each layer still needs photons, circulating water, heat removal, nutrients, access, labor, and emergency power. More layers mean more density. More density means more connections that have to keep working. Antarctica proves that skilled people can inhabit an extreme outpost, while a productive planet stands behind them. The greenhouse succeeds because ships, fuel, farms, factories, and evacuation routes still exist beyond its walls. Remove them, and the greenhouse becomes the end of a much longer chain. That longer chain would have to stand behind every greenhouse on Mars. The area alone gives a first glimpse of it. At a planning value of 50 square meters of controlled crops for each person, 8 billion people would need about 400,000 square kilometers of growing space, around 1.64 United Kingdoms. That figure has already appeared because it matters, but it can mislead us if it sounds like a land claim. It is not. Every square meter would be a managed machine. Roots, water, nutrients, pipes, filters, sensors, air moving through leaves, heat moving out of lamps, workers repairing the pieces that keep all of this alive. One claim sometimes attached to this calculation says the farms would use 9 times the world's electricity. We cannot treat that as a verified answer. The total changes with diet, crop choice, lighting, temperature, storage, redundancy, and the edge of the system we choose to count. We do not know the final number. But the uncertainty does not make the system small. Consider water. One planning example assigns 50 litres to each square metre of crop area. That is 51-litre bottles spread across every square metre, before we ask how often the water is reused. The water does not simply sit beneath a plant. It moves through root zones, reservoirs, pumps, filters, humidity recovery units, purity checks, and leak control. A farm on Mars would not merely consume water. It would keep a vast inventory circulating without interruption. Fertility creates another flow. An upper planning value of 90 kilograms of fertilizer for each person each year would become 720 million metric tons for 8 billion people. That is about 3.9 times the 185 million tons of the 3 main inorganic fertilizer nutrients used globally in 2022. This is not a Mars recipe, it is an upper bound, but it shows the kind of chemical river a civilization-scale food system might need to manage. And then the sunlight matters. Mars receives about 43% of the sunlight Earth receives, less than half. That is before seasonal angle, dust in the sky, dust on panels, greenhouse transmission, and the losses involved in storing energy for later. Direct sunlight can grow crops. Supplemental light can extend it. Fully artificial lighting can replace it. Each choice passes the same bill onward. Light-emitting diodes are lamps that turn electricity into plant-useful light. They also make heat. The farm must then cool or distribute that heat. Pumps need power. Water treatment needs power. Carbon dioxide control needs power. Harvesting, storage, processing, communications, and recovery after equipment failure need power. Free sunlight is not free food. Something else was happening. The sun is available. The farm still needs a grid. Not a garden shed supply. A survival grid. One review found that even a modest surface mission of 2 people for 30 days required at least 10 kilowatts. Think of 10 1-kilowatt heaters running together. Longer missions that include propellant production rise into the hundreds of kilowatts, and toward megawatt-class systems. That is before a city adds farms, homes, hospitals, mines, refineries, and factories. Dust makes the difference sharper. Regional Martian storms can last days or weeks. Global storms can last weeks or months. In one model for Jezero Crater, preserving only 22 kilowatts through a 120-day storm required a solar and storage system weighing 9,800 kilograms, about the mass of a school bus. In that specific comparison, a 7,000 kilogram fission system supplied full power. Fission means making heat by splitting heavy atoms. The result is firm power. Power that does not wait for clear skies. Not a victory for one technology. A reminder of the whole system. The planned 40 kilowatt class surface fission system had not yet been demonstrated as of August 2026. And even a successful reactor is not an independent civilization. It needs fuel, controls, cooling, heat rejection, security, maintenance, replacement parts, and eventual decommissioning. The order of demand would be unforgiving. Life support first, then food, then hospitals, communications, mining, refining, manufacturing, transport, homes, and reserve. A power failure would not be an ordinary brownout. Pressure falls, water stops moving, temperatures drift, food systems weaken, medical equipment loses its margin. Several emergencies begin together. Mars does have carbon dioxide, water, iron, silica, and other useful materials. Some fuels and industrial products could be made from them. That possibility is real. We should not simply say Mars has no useful fuel or no path to steel. But a feedstock is not a finished material. Carbon dioxide becomes useful only after machines capture, compress, react, separate, and store it. Minerals become useful only after excavation, heat, chemistry, shaping, inspection, and quality control. Mars does not automatically recreate Earth's hydrocarbons, metallurgical practice, or chemical industries. The greenhouse, therefore, has an upstream world. Plastics, fertilizers, lubricants, solvents, steel, seals, batteries, solar panels, pressure vessels, machine tools, laboratories, mines, transport. Each is a system behind the system. The smallest components make this visible. A semiconductor is the patterned material inside a modern electronic chip. A modern chip may require 1,000 to 1,500 processing steps and more than 300 inputs. Ultra-pure gases, specialty chemicals, wafers, very clean water, critical minerals, precision tools, contamination control. The controller on a single greenhouse pump may look ordinary. It is not ordinary. It is a compressed supply chain. A small piece of hardware carrying the work of a planet-wide industrial world. Historical colonies could send commodities into an existing Earth economy. They could trade through ports, farms, workshops, banks, and cities connected by the same biosphere. An early Mars settlement would initially export little that keeps its supplier alive. It would ask for survival-critical equipment across a distance often summarized as 54.6 million kilometers, roughly 140 trips from Earth to the Moon. That reverses the usual story. Mars is imagined as relief for a damaged Earth. Yet a civilization-scale Mars project could draw labor, clean energy, materials, and political attention from the very planet it claims to leave behind. Not a partner at first, a dependent customer, and perhaps a costly one. That dependence could last centuries, perhaps indefinitely. Partial local production would still be worthwhile. Making water, oxygen, shielding, fuel, selected food, or simple structures on Mars could make an outpost safer. But independence is a harder word. It means reproducing the machines and knowledge that reproduce the commodities. It means replacing the controller, the pump, the laboratory instrument, and the tool that makes the replacement tool. We do not know how large a settlement must be, or how long it would take to cross that threshold. Perhaps the answer lies far ahead in terraforming, changing a planet's atmosphere and surface so it becomes less hostile. But if one sealed farm already needs a second energy and manufacturing civilization beneath it, changing an entire planet is a different order of project. The hardest missing part is not always the largest machine. Sometimes it is the treatment a patient needs tonight. Small crews can prepare for that problem surprisingly well. Astronauts are selected for unusual health. They are screened before launch. They train across disciplines. A crew member can learn life-saving care, wound suturing, injections, and even tooth extraction. Suturing means closing a wound with stitches. Ground specialists can study the case, send advice, and help the crew decide what to do. For an expedition, that is sensible. The patient group is narrow. The mission can exclude many existing conditions. And somewhere behind the mission is a larger hospital system on Earth, with specialists, equipment, and a possible route home. A city changes every one of those assumptions. A complete society contains trauma and infection. It contains cancer and heart disease. It contains pregnancy, premature birth, childhood illness, disability, dentistry, psychiatric crisis, rehabilitation, chronic medication, surgery, intensive care, aging, and death. These are not failures of selection. They are ordinary parts of human life. An outpost can say that some cases are incompatible with the mission. A civilization cannot keep saying that forever. Not if it intends to include the whole human life cycle. Existing medical standards make the difference plain. When treatment aboard a mission reaches its limit, the ideal next step is evacuation to higher care. Higher care means a larger hospital with more people, more equipment, and more options. The standards also acknowledge a harder possibility. Return may be impossible, or it may take so long that it no longer helps. That is the first quiet boundary. A medical kit can stabilize. It cannot promise everything. Telemedicine seems to soften that boundary. Telemedicine is medical care guided across a communication link. A Mars patient could have Earth specialists watching scans, reviewing laboratory results, and advising a local team. That expertise would matter. It could save lives, but it cannot stand at the bedside. In crude mission analyses, a message can take 21 to 23 minutes to travel one way. That is longer than boiling a pot of pasta. Direct communication blackouts can last weeks. A surgeon on Earth may receive the question after the crucial moment has passed. The answer then begins its own long trip back. Wait. The patient may need action before the question arrives. Earth can send knowledge. It cannot perform a real-time intervention through that delay. No live instruction, no immediate second opinion, no rapid evacuation. The Mars team must already have the people, the tools, the blood, the medicines, and the decision-making authority inside the habitat. And then, the boundary becomes more serious. Medical guidance for long missions already recognizes palliative care. Palliative care means keeping someone comfortable when treatment can no longer restore survival. Severe trauma, major burns, head or neck injury, shock, when the body cannot maintain enough blood flow, radiation sickness, sepsis, a dangerous body-wide response to infection. This is not cruelty. It is an honest limit. An expedition may have to accept it. A public health promise cannot quietly build itself around it. Now the hospital appears, not as a room of beds, as an infrastructure district. It needs clean water. It needs sanitation. It needs hand washing, sterile processing, environmental cleaning, infection control, medical waste handling, oxygen, laboratories, uninterrupted power, and maintenance. Sterile processing means cleaning and preparing instruments so they do not carry infection into the next patient. Each service is ordinary on Earth because another system supports it. Hospital planning standards use about 40 to 60 litres of water for each inpatient each day. That is 40 to 61 litre bottles for one person in one day. An operating theatre or maternity intervention can require around 100 litres. Picture 100 bottles set beside a single procedure. On Mars, none of that water disappears into an outside utility. It joins the same heating, purification, recovery, and reserve system that keeps everyone else drinking. Blood makes the dependency even clearer. A blood bank is not a refrigerator holding bags. It is a small, regulated factory. Donors must be screened. Collection must remain sterile. Components must be processed and tested. Temperatures need independent monitoring. Alarms, records, backup storage, and trained workers all have to keep functioning. Red cells must stay between 1 and 6 degrees Celsius, like food held safely in a refrigerator. Frozen plasma must remain at minus 25 degrees Celsius, or colder, deeper than an ordinary home freezer. Platelets must stay between 20 and 24 degrees Celsius, and move continuously. Platelets are the blood components that help form clots. They cannot simply sit on a shelf. 3 products, 3 controlled environments, 1 fragile inventory. A power failure can close the chain. Refrigeration stops. Alarms fail. Temperatures drift. Blood is lost. Medicine has the same problem, although it is easier to overlook because tablets look durable. A study followed 35 matched medicine formulations for 28 months in low Earth orbit. More flight medicines had lower active content than their Earth controls. Active content is the part of a medicine that produces its intended effect. The loss increased with time, regardless of the labeled expiration date. Another synthesis examined 36 products stored for as long as 2.4 years. It suggested degradation, the slow loss of useful chemical strength, could occur roughly 1.5 times faster in orbit. That is like a shelf clock running 1.5 times as fast. The evidence still has major gaps, especially beyond repackaged solid tablets. We do not know how every Mars medicine would behave. Biologics, medicines made from living systems, and vaccines may need strict cold storage. A brief temperature excursion can sharply reduce their effectiveness. Sterile injectables, diagnostics, anesthetics, and reagents need more than shelves. Diagnostics are tests that identify illness. Reagents are the prepared chemicals those tests use. All of them depend on manufacturing and quality control. Mars may also create more medical demand, not less. Low gravity may weaken bone and cardiovascular systems. The cardiovascular system is the heart and blood vessels moving blood through the body. Radiation can raise cancer and tissue risk. Altered immunity may increase vulnerability to infection and reactivate dormant viruses. Dust, restricted diets, confinement, and a Martian day about 37 minutes longer than an Earth day may add respiratory, mental health, fatigue, and rehabilitation burdens. Rehabilitation means helping a body recover function after illness or injury. We do not know the full lifelong burden of living this way. That uncertainty is the point. A city would have to care for people while the experiment is still running. More doctors alone do not solve it. A city needs surgeons, nurses, pharmacists, laboratory scientists, dentists, obstetricians, pediatricians, psychiatrists, engineers, cleaners, blood bank workers, and relief shifts. An obstetrician cares for pregnancy and birth. A pediatrician cares for children. There must be enough of each that one illness, retirement, or death does not remove a whole service. Training replacements takes years. It needs schools, teachers, simulation, equipment, accreditation, and enough real clinical work to keep skills practiced. Accreditation is the process that confirms a professional and a program meet a required standard. The hospital therefore depends on education. Education depends on population, and both depend on the industries that keep instruments, utilities, laboratories, and medicines working. An outpost can screen out vulnerability for a while. A civilization cannot do that and remain complete. The hospital cannot become independent before the industries behind it do. The industries behind a hospital reach farther than the hospital walls. They reach into mines and furnaces. They reach into workshops, laboratories, machine tools, and clean rooms. A blood bank needs refrigeration. Refrigeration needs compressors, valves, sensors, controllers, metal pipes, electrical contacts, seals, and people who can test and repair them. Mars is not materially empty. Representative Martian dust contains about 58.2% silica, 23.7% iron oxide, 10.8% magnesium oxide, and 7.3% calcium oxide. Silica is the main ingredient of glass and many ceramics. Iron oxide is rust-like material. Magnesium oxide and calcium oxide are useful mineral compounds. In 100 buckets of this representative dust, more than half would be silica. Nearly a quarter would be iron oxide. Mars also has carbon dioxide. It has ice. These are genuine feedstocks. Feedstock means raw material before it becomes a useful product. But raw material is only the beginning. First comes excavation, then crushing, then sorting and beneficiation, separating a desired mineral from the rest of the dirt. Chemical separation follows. Furnaces follow. Molds, forming, machining, heat treatment, inspection, transport, quality control, and waste handling follow after that. A rock becomes glass, ceramic, metal, pipe, bearing, or pressure wall only after a long chain of work. A mine is not a factory. A factory is not a civilization. Construction may be the most plausible early success. Shipping heavy shielding from Earth is inefficient. Local regolith, the loose rock and dust covering the surface, could be bonded into blocks, shells, roads, berms, and protective layers around habitats. A berm is a raised bank of material. These are valuable uses. They may reduce what each arriving ship has to carry. That possibility should be granted. It is not trivial, but long-term strength, processing methods, certification, and behavior through the Martian environment remain engineering questions. Water makes the same distinction even clearer. Candidate ice can be shallow at selected sites, yet the uppermost 10 meters of ground still need mapping for depth, extent, overburden, and abundance. Overburden is the soil resting above a deposit. It cannot certify a city reserve. A city needs repeated production. It needs enough reserve for a failure season. Getting water from icy soil means excavation, soil handling, heat, vapor capture, purification, brine management, perchlorate handling, storage, and spare equipment. Perchlorates are reactive salts found in Martian soil. They can complicate water treatment and human use. Brine is salty water. Current machines are development steps. Batch processors handle material in separate loads. Semi-continuous processors move it through in stages. Screw conveyor dryers use a turning screw to carry soil through heat. They are not a Martian municipal utility. The picture did not hold. Mars has already made oxygen. MOXIE did it. MOXIE was an instrument on the Perseverance rover. It separated oxygen from the Martian atmosphere, which is mostly carbon dioxide. The process used pumping, compression, heat-resistant materials, and solid oxide electrolysis near 800 degrees Celsius. Solid oxide electrolysis uses a very hot ceramic device to split oxygen from carbon dioxide. 800 degrees is far beyond the heat of an ordinary kitchen oven. From 2021 through August 7th, 2023, the 17.1 kilogram instrument produced 122 grams of oxygen in total. That is about the mass of a small apple. It reached as much as 12 grams per hour at least 98% purity. 12 grams is about a tablespoon of sugar by weight. The demonstration worked. The chemistry worked. The Martian air worked. But it was a pilot kiln, not an oxygen economy. A proposed human mission generator is estimated to be around 100 times larger. One Mars ascent needs roughly 33 to 50 metric tons of fuel. A metric ton is about the mass of a large car. So a local oxygen plant is not just a box that makes a gas. As it grows, the compressors grow, thermal control grows, separation, storage, valves, power, and maintenance grow with it. And oxygen is only one half of the fuel problem. Methane production begins with water extraction. It needs electrolysis, splitting water into hydrogen and oxygen with electricity. It needs hydrogen handling, carbon dioxide intake, reactors, heat management, gas separation, liquefaction, tanks, and catalysts. Liquefaction turns a gas into a dense liquid for storage. Catalysts are materials that speed chemical reactions without being used up immediately. One local fuel source is many linked plants. The smallest parts may matter most. Life support depends on filters, catalysts, molecular sieves, pumps, valves, tanks, sensors, electrolysis stacks, controllers, seals, and software. A molecular sieve is a material with tiny pores that traps selected gases. An electrolysis stack is the layered core where water is split. A seal is the small barrier that keeps a gas or liquid from escaping. The settlement does not become independent when it can pile up the most dirt. It becomes independent when it can repair the smallest, irreplaceable part. This is where additive manufacturing enters. Additive manufacturing builds an object layer by layer from a digital design. It can make selected tools and components. It can lower the inventory of some spare parts. That is useful. But a printer is a workshop tool. It is not an industrial civilization. It does not automatically supply purified feedstock. It does not make bearings, electronics, sensors, high-performance polymers, certified designs, or the replacement parts inside the printer itself. A bearing is the precision part that lets a shaft turn smoothly. A polymer is a manufactured material built from repeating chemical units. Certification is the testing process that establishes whether a part can safely do its job. Think about a workshop on Earth. It can shape wood or metal into a useful object. But the workshop depends on bought electricity, sharp cutting tools, measured materials, replacement motors, lubricants, gauges, and the factories that made the workshop. On Mars, every one of those background supports has to be rebuilt or imported. The upper boundary is the semiconductor. A semiconductor is the material used to control electrical signals in a chip. A modern chip can require 1,000 to 1,500 fabrication steps, and more than 300 inputs. It is less like assembling one appliance and more like coordinating the specialist work of an entire city. Ultra-pure water is needed. So are specialty chemicals, gases, wafers, rare materials, corrosion-resistant delivery systems, clean rooms, metrology, and precision tools. Metrology is the science of exact measurement. A small change in a valve or chemical container can change the yield, the fraction of chips that work after production. The same recursion reaches batteries, motors, reactors, solar cells, medical devices, and machine tools. The machines must maintain the machines that maintain the machines. And the knowledge must be maintained too. Training, test standards, repair practice, and redundant production paths all matter. Recycling helps. It lowers imports. It does not close the loop perfectly. Metals corrode, polymers embrittle, catalysts foul, nutrients disperse, chips fail. Mixed waste loses purity. Every cycle needs energy, makeup material, quality control, and trained people. So there are 3 different claims. An outpost imports almost all high-value systems. A partially self-reliant settlement makes water, oxygen, fuel, shielding, simple structures, selected food, and some spares. A replacement civilization maintains utilities, medicine, industry, education, and population after Earth resupply stops. Existing studies describe small science bases, larger bases with partial closure, and settlements with manufacturing and nuclear power. They do not demonstrate the final stage. Mars is a promising place to learn local production. It remains an unproven place to reproduce modern civilization. And even a civilization with working machines needs something more difficult to replace. It needs generations who can live there. But a civilization has another replacement cycle: population. Machines can maintain machines, a settlement can repair a pump, recycle water, and keep a pressure wall standing. But a replacement civilization must do more. It must support conception, implantation, pregnancy, birth, childhood, puberty, adulthood, aging, disability, and death. It must do this again and again across generations. Keeping trained adults alive for a tour is one achievement. Continuing humanity is another. That difference leads back to gravity. Mars has 0.38 g. It has more pull than orbit, but far less than Earth. We know that much. What we do not have is a known line between too little gravity and enough gravity for a whole human life. The evidence from adults points in one direction. In microgravity, astronauts lose about 1 to 1.5% of weight-bearing bone density each month during missions lasting 4 to 6 months. That is roughly 1 or 2 pieces gone from every 100, month after month, through a season or half a year. Bone is living, load-bearing structure. It rebuilds itself in response to demand. Remove much of the demand, and the rebuilding slows. Muscle changes too. So do the heart and blood vessels. Circulation shifts. The immune system changes. Eyes, balance, and brain structures can change as well. None of this tells us exactly what Mars does to a person. It tells us that gravity is not background scenery. It is part of the body TM's operating environment. And the most important range is the least studied. Between 0.1 and 0.4 g lies the pull of the Moon and Mars. That is between 1/10 and 2/5 of Earth at TM's pull. Some researchers expect that more than 0.5 g, more than half of Earth layer TM's pull, may be needed for adequate loading. But expectation is not a human threshold. No experiment has drawn that line. Mars is not weightlessness. It is not Earth either. It is the unanswered middle. That is the first biological gate. A person may arrive at 0.38 g with an adult body already built under Earth gravity. But can a body grow there? Can it heal there? Can it age there? Can it later carry its own weight on Earth? We do not have the answer. Exercise can reduce some adult losses. So can bisphosphonates, medicines that slow the breakdown of bone. These are valuable countermeasures. They are not a proof of development. An astronaut can follow a demanding schedule. A fetus cannot. A child cannot always. A sick person may not be able to. An older adult may not be able to. A society cannot base its future on everybody performing an elite astronaut regimen forever. Artificial gravity offers a fairer possibility. A rotating spacecraft or centrifuge could press a body outward against a surface. That outward pressure can imitate some effects of gravity. It might help protect bone, muscle, circulation, and the sensoromotor system, the body and TMS coordination of movement and balance. But rotation is an environment. It is not a gravity switch. The needed gravity level is unknown. The needed radius is unknown. The rotation rate is unknown. So are the duration and frequency. A small rotating space can create Coriolis forces, the sideways sensation that appears when you move through a spinning system. It can create vestibular illusions, errors in the inner ear TNM's sense of balance. Motion sickness may follow. Injury risk may follow. So can a difference in pull between the head and feet. No long-duration human experiment now gives us Mars gravity in a centrifuge and watches an entire life unfold. The tool may become important. It remains unvalidated for the work being asked of it. Then comes reproduction. Here, the evidence becomes thinner still. A 2024 systematic review found only 16 eligible human studies of reproductive health in space. Only 5 involved female participants. 16 studies is a small research shelf. 5 studies fill only a corner of it. And no human pregnancy has been studied in space. This is not a blank detail. It is the central question. Cells and animals can show where concern may lie. High charge, high energy particles can damage ovarian follicles, the small structures that contain immature eggs, and spermatogenic cells, the cells that make sperm. Simulated microgravity has disrupted sperm navigation, sperm production, and testosterone production in some models. These results matter, but they cannot tell us the fate of a human child on Mars. Mouse embryos have reached the blastocyst stage in orbit. A blastocyst is an early ball of cells, formed only days after fertilization. That sounds encouraging. It is also where the certainty ends. Not a birth, not a childhood, not a generation. Blastocyst formation was lower in both microgravity and artificial 1G space conditions than in ground controls. 2 published embryo experiments also disagree about DNA damage and embryo quality. One early milestone is real. The lifetime conclusion is not. Short rat gestation studies found early changes in balance and the vestibular system, with some later recovery. Yet no animal study follows a complete human-like life cycle at Mars gravity under Martian radiation. Not conception through birth. Not birth through adulthood. Not adulthood through the next generation. Radiation adds another uncertainty to every stage. On the Martian surface, sighted measurements found about 0.64 plus or minus 0.12 millisievert each day. A millisievert is a measure of radiation dose to living tissue. During cruise, the sighted measurement was about 1.84 plus or minus 0.3 millisievert each day. Rapidly dividing cells may be especially vulnerable. Reproductive cells divide, embryos divide, fetuses divide, children grow. The concern is not a credible forecast of a particular Mars-born risk. We do not have one. The concern is that early damage can travel through an entire lifetime, while the relevant lifetime has never been observed. And then comes the return problem. A person born on Mars would develop beneath 0.38 G. Earth would be the first full gravity environment that body had ever known. The bones, muscles, heart, circulation, and balance system would meet 1G all at once. Perhaps that body could adapt. Perhaps it could not. We do not know yet. The settlement might create people for whom ancestral Earth is medically inaccessible, not because they failed, because their bodies formed somewhere else. This is why the ethical sequence cannot be made easy. Waiting for generational proof may mean waiting forever, because the proof requires generations. Proceeding means children who cannot consent would live inside the experiment. The risk may be manageable, it may not be. The permanent consequences are unknown. There are 3 separate gates: rotating adult crews, adult settlement survival, healthy multi-generational civilization. Passing the first does not pass the second. Passing the second does not pass the third. And before any generation can wait for those answers, it must still live inside the seals that Mars has never agreed to remove. There is one imagined escape from all these compartments: change Mars itself. If the planet could be warmed, thickened, watered, and made breathable, perhaps the pressure walls would become temporary. The suits could come off. The farms could open. The shelters could become ordinary buildings under an ordinary sky. That is the promise of terraforming, reshaping a whole planet so that human life needs fewer machines around it. But Mars begins far from that condition. Its surface pressure is about 0.6% of Earth's. Its air is roughly 95.3% carbon dioxide. In every 100 molecules, about 95 are carbon dioxide. Surface water cannot remain open for long. It freezes, or it evaporates into the thin air. For stable open water, Mars would need a much thicker greenhouse atmosphere. A greenhouse atmosphere holds heat near the ground. One study framed the needed carbon dioxide pressure as near Earth's entire atmospheric pressure. Mars already has carbon dioxide. Its polar caps hold some of it. Warm those caps, and the frozen gas would return to the air. That sounds like the beginning of an atmosphere. It is only a doubling. Pressure rises from about 0.6% to about 1.2% of Earth's. The number doubles. The basic condition does not. Not a nearly finished atmosphere, a slightly less thin one. The soil seems to offer another reserve. Martian dirt can hold adsorbed carbon dioxide, gas clinging to grains and pores. Heating that material might provide up to 4% of the pressure needed for major warming. But it would mean processing the planet to roughly 100 yards deep, about the length of a football field beneath almost every place you could stand. And that is the favourable estimate. Shallow carbon-bearing minerals do not appear to contain enough material either. Deeper deposits might hold more. We do not know their full extent. Recovering them may require heating rock above 300 degrees Celsius, hotter than an ordinary household oven can reach. Water vapor cannot quietly solve the problem from the other direction. Water vapor is a greenhouse gas. It can hold heat, but Mars is too cold to keep enough of it in the air before the warming has already begun. Local ice remains valuable for a settlement. It is not automatically a planetary climate system. There are more ambitious ideas. Fluorine-based greenhouse gases can trap heat very effectively. A model found that about 0.2 Pascal of an optimized mixture might destabilize the polar carbon dioxide. A Pascal is a measure of pressure. This is an almost weightless push, far gentler than the pressure of a light breath. Yet even that would be a starting mechanism, not a finished world. Those gases must be manufactured on a planetary scale. They do not last forever. And they do not provide the missing mass of air, oxygen to breathe, or nitrogen to dilute that oxygen safely. Wait. Warming is not breathing. A 2026 systems analysis examined a representative case with 20 millibars of accessible carbon dioxide. 20 millibars is only 1/50th of Earth's average surface pressure. The result was less than 10 Kelvin of warming, about the difference between a cool room and a comfortably heated one. Mars would still be Mars. The mass behind even small pressure changes is immense. Each added millibar around the whole planet needs about 3.89 quadrillion kilograms of atmosphere. That is the mass of 3.89 quadrillion 1-litre bottles of water. Useful open surface inventories climb into the range of 10 to the 17th and 10 to the 18th kilograms. Then comes the atmosphere people would actually need. One human open model uses 21 kilopascals of oxygen, about 1/5 of Earth's sea level pressure, and 50 kilopascals of nitrogen, about half of that total pressure. Nitrogen is the buffer gas. It is the non-oxygen part of the air that keeps oxygen from becoming dangerously concentrated. That model needs about 9.0 times 10 to the 17th kilograms of oxygen. It needs about 1.9 times 10 to the 18th kilograms of nitrogen. The oxygen alone matches 900 quadrillion 1-litre bottles of water in mass. The nitrogen is more than twice that mass again. Making the oxygen from water would require at least 1.3 times 10 to the 25th joules before losses. A joule is a unit of energy. Here the account contains 25 zeros. Nitrogen remains a separate inventory to find, extract, process, and hold, and the other proposals move the burden. They do not make it disappear. Orbital mirrors could reflect more sunlight onto Mars. One analysis places their required area between 10 to the 13th and 10 to the 14th square meters, a shining sheet spread across 10 to 100 million square kilometers. The aim is a mean temperature between 250 and 273 Kelvin, from about minus 23 degrees Celsius to the freezing point of water. Redirecting volatile, rich bodies would mean guided planetary impacts. One assessment required many thousands. Natural volcanic outgassing is quieter still. Even if atmospheric loss stopped, it would take about 10 million years to double the present atmosphere. 10 million complete turns of Earth around the Sun. Terraforming is often described as an energy problem. Heat the planet, release the gas, let the climate respond, but the real inventory is wider. Heat, total pressure, oxygen, buffer gas, radiation protection, ecology, retention. Each has its own material, each has its own machines, each has its own failure mode. Mars also lacks a global intrinsic magnetic field, a planet-wide magnetic shield generated inside the world. Solar wind, the constant stream of particles from the sun, has helped remove its ancient atmosphere. Sputtering, particles knocking other particles upward and away, is estimated to have removed about 65% of Mars's original argon. Nearly 2/3 gone. The process is still not merely ancient history. During the 2018 global dust storm, water rose to at least 80 kilometers above the surface. That is 80,000 meters into the sky. There, sunlight can split water molecules apart. The lighter pieces can escape. A deliberately thickened atmosphere would need a credible way to protect itself, replenish itself, or accept a known loss rate. No such complete strategy arrives simply because the planet becomes warmer. Partial change may still matter. Larger enclosed zones could make local work easier. Para-terraforming, creating controlled environments within an otherwise hostile world, may reduce some burdens. But the pressure walls remain. The radiation shelters remain. So do nutrients, industry, repair, and life support. No agreed timetable tells us when Mars could become Earth-like. The stronger conclusion is simpler. Present accessible inventories and present technology do not produce that world. The constraints run from mining a planet to waiting through million-year natural processes. So, the migrants must build and sustain a sealed civilization before they can begin the planetary project meant to make sealed civilization unnecessary. And while that enclosure remains, someone must decide how its air, water, power, and risk are shared. And while that enclosure remains, someone must decide how it is run. Air is a controlled flow. Water is a controlled flow. Electricity, food, shelter, medicine, transport, and access to Earth are controlled flows too. On Mars, every technical allocation becomes a decision about rights, work, risk, and power. Who may use the reserve? Who repairs the failed unit? Who waits? Who gets sent home? That is politics. Even before anyone calls it politics. The legal floor already exists. In 1967, the Outer Space Treaty said that no nation may claim a celestial body by sovereignty, use, occupation, or any other means. Mars cannot simply become a national territory because a nation arrives first. But the treaty does not create a city constitution. It does something narrower. It holds states responsible for their national activities, including the activities of private organizations. A state must authorize them. A state must continually supervise them. So an early settlement does not enter a legal blank space. It arrives carrying sponsors, regulators, contracts, and Earth jurisdictions. Jurisdiction means the legal authority to make and enforce decisions. That authority may be divided before the first permanent street exists. The seam appears in the registry rule. The state that registers a space object retains jurisdiction and control over that object and its personnel. A space object is a craft, habitat, or other machine formally entered into a national record. Imagine one base built from joined modules. One module may follow one national system. The next may follow another. Their equipment may have different rules. Their workers may have different dispute paths. Their residents may answer to different sponsors while sharing the same air loop. The walls join, the law may not. Article 9 adds another layer. It calls for due regard, meaning that one activity must take serious account of the effects it could have on others. It calls for consultation when an activity may cause harmful interference. It also requires care against harmful contamination. Those words become physical on Mars. A team searching for possible Martian life may want a site kept clean. A mining team may need the ice below it. Habitat builders may need the same terrain. People traveling between them may need access. Planetary protection, the effort to avoid confusing or damaging possible Martian biology, is not separate from settlement planning. It is part of the argument over where people may dig, build, travel, and leave waste. The Artemis Accords, established in 2020, try to offer a practical framework. They treat resource use as compatible with treaty obligations. They propose notification, coordination, and temporary safety zones around activities. A safety zone is meant to reduce dangerous interference. It is not territorial ownership. And that leaves much unanswered. Property, taxation, criminal law, labour rights, elections, the accepted right to govern. Not a finished charter. A set of boundaries around one. The deepest change comes from light time. Mars can be about 4 to 24 minutes away by radio in one direction. 4 minutes is enough time for a kettle to begin boiling. 24 minutes is a short walk through a neighbourhood. An urgent question sent to Earth, then answered from Earth, can take 8 to 48 minutes. That is longer than a kettle boiling at the low end, and nearly a school lunch at the high end. During a planning meeting, that delay may be tolerable. During a pressure loss, a spreading fire, a new pathogen, or a power decision that threatens a hospital, it is not. A commander cannot wait for permission while the condition changes. Mission control may still supervise, it may still advise, it may still control supply and money, but real-time government becomes physically impossible. Not a delay in convenience, a delay in command, not distant advice, local responsibility. That is emergency sovereignty. It means local operators must make decisions with the force of government before they possess formal political sovereignty. The person who opens a valve, isolates a room, orders a quarantine, or redirects greenhouse power has acted on everyone else. And then scarcity turns every choice sharper. During a leak, who receives reserve oxygen? During a dust storm, does power go first to the greenhouse or another essential system? Who receives scarce medicine? Who gets larger living space? Who takes the dangerous work? Who gets a seat on the next Earth vehicle? Who may expand a family when every new person changes food, water, room, medical care, and reserve capacity? These are not predictions of inevitable tyranny. They are the questions that physical limits force into the open. A fair answer may exist, but it must be designed, explained, monitored, and challenged. Otherwise, a ration schedule becomes a silent form of rule. The selection begins even earlier. Seats are scarce before the settlement has elected anyone. Someone may choose migrants by wealth, nationality, health, age, fertility, skill, ideology, or sponsorship. Those criteria can shape inequality before the first habitat is assembled. The first local vote cannot easily undo who is allowed to arrive. Reproduction is the most intimate version of the problem. The settlement must balance unknown biological risk and finite life support against bodily autonomy, the ability to make personal decisions about one's own body and family. Any population rule may begin as survival planning. It can become control over intimacy. Small analogues show only part of this picture. Hera has used a 650 square foot habitat, about the floor space of a large garage, for 45 days. Chape has placed 4 people in 1,700 square feet, roughly the floor space of a large home, for a year-long simulation. Studies of 5 4-person crews can reveal work disagreement, interpersonal tension, and breakdown. They cannot predict a city across generations. They cannot tell us how families, property, class, policing, elections, or dissent will work when no one can step outside for relief. Biosphere 2 offers a limited warning. In 1991, 8 healthy people entered a materially closed system intended to last 2 years. The system had plants, equipment, rules, and managers. Then the oxygen declined unexpectedly. Intervention was required. The ecological problem and the organizational problem became tangled together. Not only a pump and crop problem, a shared political commons. The atmosphere belonged to everyone, yet its performance depended on decisions made by particular people. Colonial history can sharpen the point if we use it carefully. The American colonies breaking with Britain is vivid. It is not a law of history. Some self-governing dominions moved toward legislative independence through negotiation, including the Statute of Westminster in 1931. Mars may produce resentment without producing a war of independence. Residents may resist rules written by people who do not breathe their recycled air. Earth may remain indispensable for chips, medicine, expertise, and new people. Distance can make authority feel distant. Dependence can make separation dangerous. The relevant combination is not freedom alone. It is distance plus dependency. A settlement may want autonomy because its residents bear the immediate risk. It may still lack an independent economy, a breathable territory, and a living biosphere outside its walls. Political defiance can collide directly with the systems that keep people alive. This is the operational constitution. Whoever can ration, repair, quarantine, override, or shut life support holds immediate power. Valves matter, schedules matter, access keys matter, repair authority matters. Governance must therefore become part of mission assurance, the planning that keeps a mission safe and able to continue. It needs clear emergency authority, fair procedures when emergency power is used, transparent ration rules, independent monitoring, a way to resolve disputes, protected space for recovery, zoning, separating incompatible work and living areas, redundant systems, rehearsed transfers of power. No current international framework supplies the complete version. Voting, property, work, crime, dissent, mixed jurisdiction families, reproductive autonomy, ecology and evacuation priority all remain open. The pressure walls will arrive first. The Constitution will have to catch up behind them. The Constitution is written by people. A new planet does not deliver a new species. The people deciding who opens a valve, who receives a ration, and who holds an access key carry their habits, hopes, fears, and institutions with them. That does not mean people are fixed. History changes people. New conditions can change what communities build. But changing location alone provides no demonstrated reason to expect fairer incentives, lower consumption, or wiser cooperation. The burden of proof remains. We can see why in the record already behind us. The Anthropocene is a descriptive term for a period in which human activity acts with geological force, changing the physical systems of a planet. Its formal place in the geological timescale remains unsettled. The descriptive idea is still useful. Human systems now leave marks in air, water, land, and life that can be measured far beyond any one city or generation. The Great Acceleration is one name for this pattern. It describes the rapid recent rise of industrial activity and its connected effects. More extraction, more energy use, more production, more waste. Emissions rise, the atmosphere warms, oceans absorb carbon dioxide and become more acidic. Habitats become fields, roads, mines, and cities. Wildlife declines. None of these changes came from a single choice. They came from many ordinary choices repeated through powerful systems. The source gives a few markers. Atmospheric carbon dioxide is about 50% above its level before the Industrial Revolution. For every 2 parts in the older atmosphere, there are now about 3. The ocean has become about 30% more acidic from absorbed carbon dioxide, an increase of nearly 1/3. Humans have converted 44% of habitable land to agriculture. That is just under half of the land where people could realistically live and grow food. The source also gives a broad wildlife loss indicator of 60% since 1970. More than half in the source measure. It must not be treated as a claim that 60% of all species or every kind of animal has vanished. The definition matters. Those figures do not prove that humans are uniquely destructive. They show something more practical. Large societies can turn abundance into pressure when their incentives reward extraction and postpone the cost. And then the question changes. What would happen if that same capacity arrived on Mars? Mars looks clean from Earth because no industrial civilization has lived there. Its plains have no highways. Its sky has no aircraft trails. Its soil has no centuries of industrial waste. This can feel like a fresh beginning, but clean is not the same as ready. Keeping billions alive would begin with mining, power generation, construction, chemical processing, waste management, scarcity allocation. Every glass of water would come through machines. Every breathable room would depend on an air loop. Every crop would grow inside a managed system. Mars would not receive a civilization after it became safe. The civilization would be the process of making it safe. Not an untouched refuge, a working environment, not a distant environmental problem, an immediate local one, and not much natural buffer. Earth can disperse some pollution through its vast atmosphere and hydrological cycle. The moving system of oceans, clouds, rain, rivers, and groundwater. That dispersal does not erase damage. It can spread damage across whole regions and generations. But it does provide scale, dilution, and living systems that no Martian settlement begins with. On Mars, contamination in an air loop, a crop system, a water mine, or a habitat can return quickly to the same population that created it. A fault in a nutrient tank does not drift beyond the horizon. A waste problem does not wash into a distant ocean. It comes back through the pipes, through the food, through the air. That visibility might encourage more discipline. It might make waste harder to ignore. We do not know. But visibility does not guarantee cooperation when risk is unequal. One group may live nearer the machinery, another may control the safest rooms. One group may bear the dust, repair work, or ration cuts. Another may make the decisions. The closed world makes the connection visible. It does not automatically make power fair. The same caution applies to the claim that 8 billion people would inevitably ruin Mars. We cannot know that. A Martian society might create institutions unlike any on Earth. It might develop stronger shared rules, because survival is so clearly mutual. But a new address is not evidence of a new incentive system. The consequence of failure simply becomes more immediate. Distance adds another pressure. The American colonies and Britain show one powerful example of a distant population challenging a distant authority. But rebellion is not a universal rule. Other colonies reached negotiated independence or remained associated in different ways. The useful lesson is narrower. Distance and local danger can change what authority feels legitimate. Mars residents may resent rules written by people who do not breathe recycled air. Earth populations may resent supporting a settlement that still needs supplies, expertise, and investment from home. The separation could become political, it could become economic, it could become personal, and it would unfold inside a world where a disagreement can touch power, food, water, shelter, and repair. This is the inversion at the center of the dream. From inside a struggling Martian habitat, even a damaged Earth may look almost impossibly generous. Open sky, oceans, rain, soil, wildlife, full gravity, breathable pressure. A recovering Earth may still look green. It may still look like paradise. That does not make exploration immoral. It does not prove that Mars institutions must repeat every failure of Earth. It says only that migration adds environmental and political stakes without solving the institutions, inequality, consumption, conflict, and incentives that made escape seem necessary. From inside that sealed world, the comparison becomes harder to avoid. From inside that sealed world, the comparison becomes very simple. Earth is the easier world to save. That does not mean repairing Earth would be cheap, simple, or politically easy. It is none of those things. Nor can we settle the question by placing one large number beside another. There is no credible common price for restoring every damaged Earth system and building a replacement civilization on Mars. The two projects do not yet have comparable totals. So compare what each world supplies. Compare the services already running before any human decision is made. Start with the air. Earth gives us an atmosphere at a pressure our bodies can live in. It is about 78% nitrogen and 21% oxygen. Roughly 4/5 of the air is nitrogen, and about 1/5 is oxygen. Together, at the right pressure, those gases make an outdoor human life possible. The atmosphere also absorbs much harmful radiation, and it burns up most small meteoroids before they reach the ground. Mars begins elsewhere. Its atmosphere is about 95.3% carbon dioxide. Its pressure is less than 1/100th of Earth's. The difference does not wait for a distant ecological crisis. It is present at the habitat door. Anyone who goes outside must carry pressure, oxygen, temperature control, water, communications, and protection. A spacesuit is not ordinary clothing. It is a personal spacecraft. Then comes the shielding. Earth has a global magnetic field, a planet-wide field that deflects many charged particles from the sun and from deeper space. Its thick atmosphere adds another layer of protection. Together, they also help Earth retain the air it already has. Mars has no comparable global field. A Mars settlement must compensate with mass shielding, storm shelters, radiation dose measurement, construction work, and an acceptance that some long-term health risks remain uncertain. This is not one missing convenience. It is a service that has to be built, then watched, then repaired. Water makes the contrast even clearer. Earth has oceans, clouds, rain, rivers, groundwater, land, and living systems connected by sunlight. The water cycle is a moving circulation system powered by the sun that shifts water between all of those places. It is not perfect. It is already under pressure, but it is immense, distributed, and already operating. Mars has ice. That matters. But ice must be found, mapped, certified, mined, heated, cleaned of unwanted chemicals, stored, piped, kept from freezing, and recovered again after use. Every stage needs power. Every stage needs equipment. Every stage needs people who can keep it working. The raw resource is real. The public service is not. The same is true of the biosphere, the living network of plants, animals, microbes, soils, and waters. Earth's biosphere helps regulate gases, move water, build and aerate soil, store carbon, recycle nutrients, pollinate crops, and support food webs. A food web is the network of organisms that feed one another and keep an ecosystem functioning. These services are not free of damage. They can be weakened. They can collapse in places. But they exist before we begin. Mars begins with regolith, broken mineral material on the surface, hazardous salts, and no demonstrated native ecology. A Martian farm would need to manufacture every useful condition: light, water, nutrients, temperature, pressure, purity, pollination, or an alternative: waste treatment. The crops would grow inside a machine supported by other machines. Gravity belongs on that same ledger. Earth's gravity is 9.81665 meters per second squared. It is the familiar full pull that has shaped every human body and every human generation. Mars is 3.71 meters per second squared, about 38% as strong, less than 2/5 of the pull we know. We do not know whether that environment can support an entire human life, from development before birth through childhood, adulthood, illness, aging, and the next generation. Repairing Earth does not require us to discover what gravity a child needs. And then there is inherited civilization. Earth already has cities, hospitals, schools, roads, ports, power grids, farms, mines, factories, laboratories, data networks, governments, trained workers, and billions of social relationships. These systems fail unevenly. They exclude people. They damage ecosystems. They need repair and reform. But they are there. A damaged Earth still begins with a living platform and an accumulated civilization. Mars must import or recreate every layer while its residents remain inside life support. Air has to work while a hospital is built. Water has to work while a school is taught. Power has to work while factories learn to make replacement parts. Food has to work while a government decides who receives it. The city cannot pause one system while it improves another. Every system is already carrying people. This is the central reversal. A badly damaged Earth may look grim from the ground. Mars may look clean from far away. Yet the starting platforms are not close. Earth can lose enormous ecological quality and still retain breathable pressure. It retains full gravity. It retains oceans. It retains radiation protection. It retains roads, hospitals, farms, and a biosphere that still lives. Mars begins without those foundations. It begins by manufacturing survival. That does not minimize ecological collapse. It clarifies what is at stake. The reason to repair Earth is not that it can absorb endless damage. It cannot. The reason is that its remaining planetary services are irreplaceably generous. Losing them would make every human problem harder. Keeping them gives repair a place to begin. This comparison also gives Mars projects a more honest vocabulary. A scientific outpost can rely on Earth for advanced parts, rare medicines, specialist knowledge, and replacement crews. A small settlement might make water, oxygen, fuel, shielding, selected food, structures, and some simple parts locally. Those would be real achievements. A replacement civilization is a different threshold. It must keep every critical service operating after Earth resupply stops. No authoritative population number marks that threshold. We do not know it. We also do not yet have a long-duration integrated Mars utility, a combined system that mines resources and keeps air, water, food, power, and industry working together in the Martian environment. The distinction is still clear. Presence is not independence. Local production is not replacement civilization. Mars technology remains valuable within that honesty. Closed water loops, efficient agriculture, reliable power, material recovery, remote medicine, autonomous repair, and planetary science can support exploration. They may also improve resilience on Earth, meaning the ability of communities and systems to keep functioning through disruption. The argument is not against research. It is against using research as proof that mass substitution is ready. And repair has real places to start. More compact settlement, public and active transport, efficient buildings and retrofits, improving existing structures so they waste less energy, lower material demand, low emission electricity, conservation and restoration of ecosystems, food systems that use resources more carefully, less food lost between field and plate. None of that is a small task. Maintaining biodiversity and ecosystem service resilience may require conserving roughly 30 to 50% of land, freshwater, and ocean areas. In plain terms, 3 to 5 parts of every 10. The work would be immense, but it would be work done on a planet with breathable air, flowing water, full gravity, living soil, industrial capacity, and people already spread across its surface. The cooperation test returns us to the beginning. A century-scale evacuation would demand international planning, shared standards, enormous clean energy, new industries, disciplined allocation, and long-term thinking. It would demand millions of launches, closed cities, planetary mining, and generations of artificial life support. Those are extraordinary capacities. On January 9th, 2013, Neil deGrasse Tyson made the comparison plainly. A civilization capable of turning Mars into something like Earth would also be capable of repairing Earth's oceans and atmosphere. This is not a cost estimate. It is a capability argument. If we can organize the harder project, then part of that same organization can serve the living world already beneath our feet. Not because Earth repair is effortless, because Mars replacement is harder. Not because Mars has no value, because dependence is not a lifeboat. And not because the future must remain on one world. Because moving a significant share of humanity to a dependent Mars is not a credible substitute for repair. That is what no Plan B means. It does not mean no Mars science, no base, no settlement, no long-term off-world future. It means that valuation, ambition, and exploration hardware do not prove that public evacuation systems exist, are financed, or are preferable to direct resilience. It means we should not call a dependent outpost a refuge for 8 billion people. Moving humanity to Mars adds transport, biological, ecological, industrial, medical, and political problems to the crisis that sent people looking upward. Repair works at the source while preserving the planetary life support that no engineering program has to build from zero. The barriers are real, the political choices are hard, but the starting world is still alive. There is one kind of danger for which repair cannot be the first answer. There is one important exception to that repair first argument. Some dangers do not begin with human neglect. An asteroid impact severe enough to collapse civilization or make Earth broadly uninhabitable cannot be repaired before it arrives. Afterward, may be too late. The source even allows the possibility that a small asteroid could disrupt the climate and reduce civilization towards Stone Age conditions. Small is not defined. Neither is the threshold. That uncertainty matters. This is the strongest case for asking whether humanity needs another world. It is also where the first answer becomes clearer. Find the hazard early, then move the hazard. With enough warning, an approaching object may be deflected or disrupted. Deflection means changing its path so that it misses Earth. Disruption means breaking or altering it so the original impact threat changes. With late detection, the available technique may not be ready. A launch may not be ready. There may simply not be enough time. That changes the order of the problem. Not people first, the object first. Not a planetary evacuation. Planetary defense. Chicxulub shows why that distinction is serious. The impact rapidly changed the climate. It ended the non-avian dinosaurs. It redirected the path of evolution. Earth did not need a second home in the moment after impact. It needed the impact not to happen. And this is no longer only a thought experiment. On September 26, 2022, DART struck Dimorphos. DART was a kinetic impact mission, meaning a spacecraft deliberately hit a small asteroid companion to change its motion. The final analysis in 2024 found that its orbital period changed by 33 minutes and 15 seconds, about the length of a short drive across town. The change was measurable. The method worked. The path moved. But the reality was different. This was not a finished planetary shield. It was a demonstration. A real one. An important one. Yet the uncertainties remain around detection coverage, warning time, readiness, and whether a kinetic impact can be used reliably against every future threat. The strongest argument for evacuation, therefore, becomes an argument for seeing earlier and acting sooner. That is the first layer of resilience, the ability to withstand danger without moving the population away from home. There may be a second layer. A small, durable, self-sufficient population away from Earth could preserve people, knowledge, and institutions if planetary defense failed. That possibility gives real meaning to long-term diversification. It supports exploration. It may support settlement. It gives a careful off-world future a serious purpose. But a base is not automatically a backup. A base supplied by Earth fails when Earth fails. A base that needs Earth for replacement parts, advanced medicine, trained specialists, industrial inputs, or new crews has not escaped the threatened world. It remains connected to it by a long and fragile line. That is the hard condition. Independence, not presence. Continuity, not a flag. The difference between backup and evacuation is therefore decisive. Evacuation tries to move the endangered population after the danger is known. It is a lifeboat launched after warning. Backup establishes a far smaller branch before the crisis, and makes that branch capable of surviving without the world in danger. The two ideas are not close. One asks how to move 8 billion people through an interplanetary transport system that does not exist. The other asks whether a much smaller population can someday maintain air, water, food, healthcare, industry, families, knowledge, and fair government without Earth. That is still an immense challenge. It is also the only version that deserves the word backup. None of the earlier barriers disappear. The branch would still need sealed life support. It would still need hospitals and manufacturing. It would still need to answer the question of children in Martian gravity. It would still need institutions that can endure scarcity without turning survival into permanent rule. A smaller number does not make these obligations small. It makes them imaginable. So the asteroid exception narrows the conclusion. It does not reverse it. Mars may become part of a long human future. It may become a place where science deepens, where new tools are tested, and where a truly independent branch is slowly built. But moving billions to a dependent Martian settlement remains neither a workable evacuation nor a substitute for the living planet beneath our feet. Defend Earth first. Repair what can be repaired. Explore and build carefully elsewhere. and reserved the word backup for something that can stand alone. The work of defense, repair, and honest diversification continues.